We're going to continue using our Pokemons today, folks. I know some of you found this to be very uncomfortable, especially those on Zoom. Now, considering that many of you are on Zoom, presumably because you really don't want to be in class because you're afraid that I might pick on you and ask you questions. But the fact is, at the end of the day, I'm here to teach you, and I have objective ways of quantifying how much I have actually conveyed to you. And one of the ways that I can quantify this is through your average quiz scores, but not just the quiz score, because all of you can manage to get a 10 if you spend 6 hours going through the slides. It's how much time you spend on the quiz. And well, if staying awake through 90 minutes of class, which you're supposed to do anyway, saves you 90 minutes of quiz time on a Saturday, I think it's a good trade-off, right? And so we will check after 2 or 3 weeks to see if this has indeed improved your quiz timings and your quiz scores. And if it has, or if it has improved even a little bit, we'll stay with it. Otherwise, I'm making you uncomfortable for no reason at all, right? So anyway, questions from the last class? Yes?
I have a question about the Pokemon. Would you consider not switching the Pokemon each time so you don't memorize a new name?
We can do that. It's just that we're still setting ourselves up, right? I think, but do you guys agree with the theory of the Pokemon? Right? I have actually had some emails from students who thanked me because they said they're being forced to pay attention. And some students really do want to pay attention, right? We are all easily distracted. You're sitting there on the other side of Zoom. Even in class, how frequently does your mind wander? All the time, right? I know my mind wanders and I'm out here. If somebody would call out my Pokemon, it would help me in class. So, yeah. Questions from last class? No. We're going to begin today's class with a story about cats. What did we discuss? What was the last thing we discussed in the, or what was the topic we discussed in the last class? Magneton. Pokemon Magneton. Okay. Miltank. You see? Okay. Pokemon Mook. What was the topic we discussed in the last class? Pokemon Poochyena. I'm beginning to embarrass myself. My first 4 Pokemons are absent. Pokemon Lugia. Pokemon Yanma. Does somebody else find this embarrassing?
It was scanning for patterns.
Scanning for patterns, right? Yeah. That's my 7th Pokemon. Guys, this is class. I am here at 8 a.m. I'm 30 years older than you. It's incredibly hard for me to wake up in the morning. I have my friend there who's my colleague, and she can vouch for this, right? And she has to drop off kids in school. And so if at your age you can make it to class in the morning, that you're supposed to. I get paid to be here at 8 o'clock. You pay to be here at 8 o'clock. And after that, if you don't do it, it's kind of embarrassing, right? It's like going to a store, paying them $1,000 for your fridge and saying, okay, let it be. It's kind of idiotic. Be here. And I'd like to remind you that every single class, you pay $300. Every single class. That's how much the fees at CMU are. You may not realize the value of $300, but those of you who are from India and China, you know that your grandfather's annual salary, I'm not speaking of monthly salary, I'm speaking of his annual salary, was $300. Every single class that you miss, you disrespected all the folks who worked for an entire year to earn that much money. Be respectful. Be here. Right? Okay, let's continue with our story about cats. Here's a little history, right? For the longest time, I mean, we all know we see, but how does sight happen? We didn't really know. So people have been trying to understand what is the neural process of visual recognition. What is the process that connects the eye to the brain and allows us to perform recognition? And most early research was behavioral. You basically studied behavioral judgment in response to visual stimulation, visual illusions, and something called Gestalt. Our brain, all the things we think we see, we do not really see. We see very little. The rest of it is filled in by the brain. And so in that first corner picture, what do you see? You see a cube? You actually see a cube? Is there a cube? No, right? What about the second picture? Is there really a dog? Right? The last one, that's my favorite. What is that? A spiky sphere, right? There is no sphere. So you see what your brain is doing to you. You're just sort of filling things in. And this is not just true of the pictures on the screen, even here, right? And so we know all of this because people studied it for the longest time. But does this tell us how the brain really works? It tells us what the brain does, but not how it works. The first work on that was done by first significant work on that was done by these two guys, Hubel and Wiesel, 1959, which was a study in the neural correlates of vision, where they studied receptive fields in the cat striate cortex. The cat striate cortex is so named because it's a portion of the brain that really has striations, and it's the equivalent of the human V1. Again, I like to tell everybody that the human visual system is an excellent example of unintelligent design. Your nerves start out in front of the eye. They have to fold back, punch through the eye to go through the eye, which is why each of us has a blind spot. And then, where do you think they connect? If you were an engineer and you were building a visual system and you had this entire brain to work with and an eye out here, which portion of your brain would your eye connect to first? Right here. Where do you think it actually connects? Out at the back, right? So idiotic, right? That's your V1 cortex. And then the signals go there, and then they sort of flow forward. But the first perception is through the V1 cortex. The equivalent for the cat's eye is the striate cortex. And so these guys studied and analyzed the response of the cat's striate cortex. They got 24 cats, anesthetized them, immobilized them, and put them on artificial respirators. This was done with truth serum, so the cat couldn't lie anymore. And they stuck electrodes into the brain to study the cat. And here's what they did. The poor thing is now, stuck there, immobilized, anesthetized, and truthful. So, what? Sorry. And so they held the eye open, and they beamed light of different wavelengths along different orientations into the cat's eye. Now, they measured the response of the cells in the V1 cortex. This captures the immediate, the 20 millisecond response of the retinal cells. Now, here are the kinds of patterns that they actually beamed. They would take a wavelength, say 300 nanometers or whatever, move it up and down, left and right at various angles, and see when it responds. And what they found was each of the cells responded in very specific manners. A cell didn't respond to light anywhere in the eye. There's a very specific region in the eye that it responded to. And specifically, the response had inhibitory regions and excitatory regions. So if there are regions where if light falls, the cell will not respond. There are other regions where it will respond, and there are other regions where it doesn't care. So if you have uniform light all over the eye, the cell will not respond because that uniform light is also falling on the inhibitory region. It must fall on the excitatory region, not fall on the inhibitory region, and it doesn't care about what else happens. And those are the kinds of patterns they found. These are from mice. These cells actually end up responding to vertical patterns, or not vertical, but linear patterns at different orientations. And so this is a beautiful one, right? You can see that this cell responds to light patterns, lines of this kind, and they're sort of emphasized by the fact that if you go off the line a little bit, the response is actually suppressed. So here is the kind of test they ran. They'd keep the eye open, and they'd move the light in different directions. So the pictures to the left show you the direction of motion, and the pictures to the right show you the spiky neural response. And you can see that in this particular cell, it responds most when the light is in a vertical pattern, and it responds least when it's horizontal, right? And this is regardless of whether you're making a full line or just a partial line. So the conclusion, oriented slits of light were the most effective stimuli for activating striate cortex neurons. And the orientation selectively resulted from previous level of input because lower level neurons responding to a slit also responded to patterns of spots if they were aligned with the same orientations as the slit. What does this mean? That the cells, not all the cells are connected to the retina. The retinal cells are connected to a first layer of cells, and then these cells connect to a second layer of cells, and so on. And so each one of these responded, at least the early layers in the V1 cortex, they responded to these patterns, but they responded to patterns which were already discovered by a previous layer. And so they actually showed that there are two levels of processing, the so-called S cells and the C cells. The S cells found the patterns on the retina, and the C cells were the second layer that actually cleaned the response up. Here's what happens. The S cell, each S cell is actually connected to a linear arrangement of retinal cells. Now, each retinal cell actually has a circular kind of isotropic response. But by having a linear being connected to a linear arrangement, it means that that cell responds to lines in that particular orientation. But then S cells tend to be noisy. They get fooled because the retinal cells are very sensitive. Your eyes are very, very sensitive. They capture even individual photons. And so the response of the S cell had to be cleaned up. And so the S cell responses went through to the next layer of cells, which they call the C cells, standing for complex cells. S stands for simple, where a complex cell would look at a collection of S cells with the same response, and then just pick the largest of these responses. This sort of implicitly ensures that you're sort of cleaning up, right? So you're picking the strongest responses and not responding to all kinds of noisy patterns. And they also found that this actually forms a hierarchy. As you go up, you have these patterns are built up. Complex C cells connect to similarly oriented, that is, C stands for complex, built from similarly oriented simple or S cells. They fine-tune the response of the simple cell, and they also show a build-up. So the first level of FS cells sort of responds to kind of linear patterns. Then they are connected to C cells, which clean up the response. Then the next level of S cells connect to a bunch of to the C cells from the previous layer and build more complex patterns. And then they have their own, the second level of S cells have their own C cells, which clean up the response and so on. And later on, they actually they never actually told us if they killed the cats. But then they did tell us that they studied the slices of the cat's brain afterwards. So leaving that to our imagination. This kind of test wouldn't pass muster today. But then just to make things more interesting, later they did things on more things that were closer to us, and to add insult to injury, they actually said this study wasn't all that great, right? The model cannot accommodate color, spatial frequency, and many other features to which neurons are tuned. Nonetheless, this little study became the basis of pretty much all of the work that we do in vision today. The first book. Okay, time's up, guys. Pokemon Yanma. What's the answer to the question? Right.
True.
Okay.
Yeah.
Thank you.
Try the first. Yeah.
S cells find patterns and C cells clean them up, right? Were you also Yanma? That was yes, last class maybe, but that's okay. And so we have the biological plausibility, the biological model. Now let's try to computationalize it. And for that, let's move forward from 1959 to 1980, Kunohiko Fukushima, who came up with this model called, he computationalized it, but in the process, he also discovered that he realized there are some deficiencies in the model as Hubel and Wiesel described it. And this has to do with the so-called grandmother neuron. How many of you have heard of the Jennifer Aniston neuron? Can you tell us what it was?
The neuron in the area IT that fires when it's in space.
Yeah, so people with epilepsy are a gold mine for folks who work on neural analysis of visual cognition in the neural system. And that's because when they get treated, they have lesions in the brain, which the doctors try to fix. So their skulls are opened up, and they lie there in the hospital for days on end with their brain essentially exposed. And so now along come these guys, a little bit of, what can I say, ghoulish. But they find these guys with their skulls open and the brains exposed, and so now they can actually put grids of electrodes on the brain and study how these neurons respond to different stimuli. And so one of these studies had to do with showing a subject various pictures and seeing how the neurons fired. And it turned out he had one particular neuron that only fired anytime he saw a picture of Jennifer Aniston. So this is the famous Jennifer Aniston neuron. Now, there's nothing special about Jennifer Aniston. There's one neuron for every single person you do recognize. So we like to call it the grandmother neuron. There's a cell in your brain, or there's a portion in your brain that responds anytime you see your grandmother. It doesn't matter where your granny is. She doesn't have to be in the middle. She can be in the periphery, but it will fire. So if your grandmother cell fires, even if your grandmother moves to a different location in your field of vision. And so Fukushima came up with this model called the neocognitron. Now, clearly, the name neocognitron means something. That before there was a neo, there was an original cognitron. So this must have been at least the version 2, as far as I can make out. And he came up with a computational model that included S cells and C cells, as Hubel and Wiesel discovered. And in addition, he also explained the grandmother cell phenomenon. And his idea was very simple, that from the eye, that's your eye, just in case you don't realize it's an eye, from the eye you have responses, the eye is being analyzed by a bunch of what he called S cells. And an S cell, so you have several S cells, and the S cells are arranged in planes. And within each plane, you have several S cells, and all of these S cells have one characteristic. They have identical responses. So this cell here responds to exactly the same pattern as, say, this cell. What is the distinction? The distinction is that if that's your retina, each cell looks at a different location of your retina. So all of them are responding to the same pattern, but each of them is looking at a different location of the retina. Similarly, the second plane of S cells has a bunch of cells, all with identical responses. The only difference being where in the eye they are looking at. And so you have an entire layer of S cells arranged in planes, where within each plane all the cells are identical, differing only in where they are looking. Then subsequently, so this was S0, these cells were cleaned up by what he called C cells. And the C cell 2 was arranged in a plane. So corresponding to every S plane, there was a C plane. And the C cells had a specific characteristic. Each C cell looks at a region in the corresponding S plane and responds to the cells or to the activations of the cells in that region. And so now you have C0. This would be your first layer, just as Hubel and Wiesel found, of visual response. Then subsequently, so this entire thing is one simple complex layer. A bunch of simple cells followed by a bunch of complex cells following this very specific pattern of response, where within the layer of simple cells, you have several planes. Each plane is a collection of cells with identical response, varying only in where they're looking at, right? So this gives you position invariance for your grandmother. It doesn't matter where your grandmother is. The S cell is that particular plane, or the planes which correspond to features of your grandmother will fire, right? And then the next layer would also include a plane of or a layer of S cells, also arranged in planes like so. So this is your layer of S cells. And now once again, within each plane, all the S cells had identical response, just as in the first layer. The only distinction is that over here, this S cell is going to be responding to this region of the eye, which means that it is responding to this guy, and this guy, because all of them are looking at that region of the eye. Making sense? Right? And so similarly, this cell over here has an identical response to this one, but it might be looking simultaneously over here, here, and here, because all of these are looking at this portion of the eye. So every cell again is looking at a different position in the eye, but through the cells in the previous layer. And so what this means is that any given cell is looking at not just one cell in the previous layer, it's looking at a cell from every plane of the previous layer, because all of those cells in the planes of the previous layer are looking at the same position in the eye, right? And then these responses are going to be cleaned up by C cells. So this would be C1, and the C is looking at something over here and cleaning it up. Observe that the C cell's job is to clean up the response of the S cells. So a C cell is only looking at a region in the corresponding S plane. The job of the S cell is to detect patterns. The C is not detecting patterns. The C is cleaning up the response of the S cells. The S cell is detecting patterns, right? And so the S cell has to look at simultaneously at all of these previous maps. The C cell only has to look at its own corresponding map. Questions? Yeah.
Why do we have in like the first layer the same copies of all?
They're not copies of all the input. So these cells all have the same response. They're just looking at different portions of the eye. So this would, for example, if this one is looking at detecting eye patterns, this cell will fire if there's an eye over here on your retina, whereas this cell will fire if there's an eye out here in the retina.
Like all the planes will be the same, right?
No, the planes are different, but within each plane, all the cells are the same. So here, for example, this one might be looking for, so this is your eye plane, this could be your nose plane, right? And so this one would fire if it found a nose here. This one would fire if it found a nose here. That answer your question? Right, okay.
What do you mean by fine-tune exactly, like clean up? What does the C cell do exactly?
It's actually looking at a collection of cells from the S cell plane and operating on them to get some kind of a what. We'll get to that in a minute, right? Because this is a computational model, obviously. There must be formulae to it. Now, since only the pattern detectors are learnable, meaning only S cells actually have weights that can be learned. C cells have a cleanup job. There's nothing learnable. There's a fixed mechanism by which they clean up the S cell responses. And so here's how it goes. Within each simple complex module, you have a layer of S cells and a layer of C cells. The S cells are arranged in planes. So are the C cells. Each S cell actually looks at all of the planes in the previous C layer. Each C cell is only looking at the corresponding S layer. You don't even have to look at the slides. The region that the cells are looking at in Fukushima's original model, the elliptical, which is a bit of an annoying thing, but he gave us mathematical formula. So here's how the whole thing would work, right? The S cells are looking simultaneously at all of the C planes, but each C cell is only looking at the corresponding S plane. And what is this response? So he had a mathematical formula based on his analysis of whatever studies had been done until that date for how the S cells responded. And so that upper equation, which I won't bother to explain, tells you how the S cell, any given S cell, responds to all of the C cell planes from the previous layer that it sees. But then if you squint, and if you squint hard enough, that formula looks like a ReLU activation on an affine combination of the previous S cells. Now, the second formula actually, it's also ReLU-like, but it has an inhibitory bias, basically, which says that if the weighted combination of the S cells is large enough, only then it's going to fire. And if you take that to the extreme, then the weighted combination actually ends up looking like a max. Right? And so, another thing, this C cell may only be looking at a small portion over here. And so this S cell, this corresponding C cell is also looking at the same small portion. It's just cleaning up the response, right? Now, this guy here is looking at a region in the previous C cell planes, which means that it's looking at a larger region in the eye, right? And then if you similarly went to the next layer, this guy is going to be looking, if you have the next S2, this guy would be looking at regions in the C cell planes, which means it's going to be looking at an even larger region of the eye. So as you go deeper and deeper into the layers, the receptive field of the neuron, which is the region of the eye that it's looking at, and the patterns it responds to, get larger. Now, because the C cell's job is to clean up, C cells, if this C cell is looking at this guy, the next C cell doesn't need to overlap with much of this. So the next C cell sort of has almost minimal overlap with the region that the previous C cell is looking at. So as a result, the C plane is a shrinking of the S plane. After cleaning up, it sort of shrinks it. So the C cell planes get smaller. They're smaller than the S plane. So correspondingly, the next S plane is going to be smaller. So as you go through the layers, the planes get smaller and smaller. But then the number of patterns you want to detect keeps getting larger and larger. So as you go through the layers, the number of planes keeps increasing, right? And this thing was, yeah. Now these formulae have parameters. Only the S cell response is learnable. So only the S cell response has learnable parameters. And the way he learned it was through Hebbian learning. Very simple mechanism. So let's say I have all of these over here. Let's say I have all of these S planes over here, right? All of these C planes. See, yes, oh, these are the C's, okay. Now, this S cell connects to all of these planes, right? At any particular position. So if you're looking at this connection of this S cell to the position 1, 1, it's going to be connecting to the position 1, 1 of all of these planes. Learning is unsupervised. You just start the initialize the whole thing randomly. And then if you find that this thing fires, then you find which of these is the largest. And if this has the largest value, then the product of these two terms is used to increment this weight. So, but then in incrementing this weight, you're also going to be incrementing this weight and this weight. Basically, any update is shared by all of the neurons in the plane, because all the planes are supposed to have, all the neurons in any particular plane are supposed to have identical response. So it was a very simple Hebbian learning rule, right? With some resolution for conflicts. If multiple cells have the same response, then you have some logic for picking one or the other. And so you just have this S and C cell cascade. You can present it with a bunch of images. It's being learned completely unsupervised. You initialize it randomly. You use the Hebbian learning rule to learn the weights. And what happened was this interesting phenomenon that when it was presented with a bunch of character images, what Fukushima found was that the cells learned automatically to identify and segregate the images by character. So more specifically, the early layer cells found individual features, like one plane might find the first leg of A, the second plane might find the central leg of A, the third might find the third leg of A. Yet another plane might find the curve of B, and so on. And then as you went through them, these would get grouped. And when you finally got to the final layer, you would find that this, if you had a bunch of S-planes, this would fire anytime an A occurred in the image. This would fire anytime a B occurred in the image, and so on. This is without supervision. It just automatically learns to detect and cluster semantically by semantic category. And in fact, it turns out that it's actually quite robust to noise, that these cells would respond regardless of whether there was noise in the image or not. And so what he found was just having this biologically plausible model comprising S cells, which are pattern detectors, and C cells, which are cleanup cells. You are able to mimic our own ability to some extent of discovering semantically coherent objects in our visual field of view without additional supervision. So this is a pretty impressive result, right? This was back in 1981. But then so questions? Yeah.
How is position preserved in this model? Like, how do I know that the AI cell is like at the left or left?
This is all about recognition.
Okay.
That's all it is, right? An A has occurred. It doesn't matter where it has occurred. My grandmother has entered the room. It doesn't matter which door she chose, right? So, yeah.
What happens if we don't have the C cells, C layers?
If you don't have the C cells, then the cleanup doesn't happen. It responds to noise. Job of the C cells was to clean up the response of the S cells, right? So far so good. Okay, time's up. Pokemon Chinchu, what's the answer to the first question?
True.
Pokemon Porygon, what's the answer to the second question?
True.
Thank you. See, the Pokemons are waking up. Both of them are true, right? Fukushima's model is an unsupervised convolutional neural network, really. And you can add supervision, clearly, to make this actually do a job. When the problem with unsupervised models is that you have no idea what they're going to do. You would want to add supervision to make them do the specific task that you're interested in. And so now I have this Fukushima model, how can I add supervision to this model? Anybody want to take a guess? Pokemon seal? How could you possibly add supervision to this model? I don't know is a good answer. Okay?
Maybe
Lantern.
add a gradient.
Pardon me?
Add a gradient, add some label.
You will need gradient, no, but you need labels, but you need something else before that, right? What would you need before that? Anybody? Huh?
A loss.
A loss, but what else do you need? Is this performing classification? So how can you compute a classification loss?
Activation.
Activate.
Yes.
You are going to have to add a classification layer out here, correct? Because this is just about extracting features. There's nothing more happening in the Fukushima model. If I want to add supervision, now I add a classification layer. Now I'm going to get classes, and now all of you are correct. I can add a loss, I can compute gradients, I can train the model. Right? Once you explain it in this manner, then this seems kind of the obvious thing to do. So it's a bit of a shock that it took from 1980 to almost 89 or 88 before somebody thought, hey, why don't I just add a softmax layer to this and train this using gradient descent? But science is slow and then it's fast. And so the neocognitron is fully unsupervised, and the semantic labels are just automatically learned. So how do you add external supervision? There were various proposals. The Homo Atlas and Marx proposed temporal correlations. The first proposal actually came here from CMU, Kevin Lang, TDNNs, 1989. And then the thing that really became famous was Jan LeCun's convolutional neural network, where you basically added a classification layer. You had labels, and then you can just use backprop to train the network. So here's what. Now observe that there's one small thing in the convolution and the neocognitron. You have planes where you have many cells with identical response. This is the same as having a single cell with scans, is it not? And so we don't actually make many copies of the cell. We just scan, just as we saw in the last class. But that's just an engineering difference change, right? So now in the original neocognitron model, the receptive fields were all elliptical, which is kind of hard to model. So when you actually began computationalizing it and adding supervision, you made the receptive fields rectangular, because that's something we can deal with on a computer. And when you're scanning, you will stride. This stride itself becomes a variable that you can choose. And so the entire model and the actual activations end up looking like a little like the activations that were suggested by Fukushima. The S cells respond using an activation function, which works on an affine function of all of the inputs, all of the values from the previous C layer. So once again, you're going to have an S layer with many planes, right? Where the plane is now computed using by scanning, and then you had a C layer also with many planes, and then in the subsequent S layer, any particular cell would be looking at a rectangular region of all of the C planes in the previous layer. And the way its value is computed is to take an affine function of all of these values, which is what is shown by the inner summation. You're going across the planes, that's the P loop, right? And then within each plane, you're going horizontally, which is the KL loop and the K loop, and then you're going to also go vertically to scan the entire region. And that's the J loop. So you're going over all of those. You're basically computing an affine function of all of those terms, and then applying an activation sigma to it. And the C cell does something very simple. The C cell over here looks at a rectangular region here and just picks the largest value. That's the cleanup job. Everybody with me? Right, okay. And so, and the whole thing can be trained. And so this was Lanett's convolutional neural network way back when. This is demo from the late 80s, early 90s as Lanett. Back in the day, one of the big problems that we had was we actually had a postal service that worked. And lots of people would send mail. They would write down addresses. And the postal service wanted an automated system that could actually scan the address and interpret it. And LeCun was at AT&T, so they had this project. He wanted to be able to scan the image and discover what the numbers were, because these are addresses, right? And you can see from his demo that it actually does a very nice job. This was way back when, in the early 90s. And so the story so far, the mammalian visual cortex consists of S cells, which capture oriented visual patterns, and C cells, which perform a majority vote over groups of S cells. The neocognitron emulates this behavior with planar banks of S and C cells. Only the S cells are learned, the C cells are not learned. And LeCun's Lanett added external supervision to the neocognitron, where the S planes are computed by scanning that's convolution, rather than actually have many copies of the cells. And C planes are emulated by cells which look at rectangular regions and just pick the largest value. And this whole thing was called a convolutional neural network. So a CNN, we spoke of where CNNs came from a computational perspective, from the scanning perspective in the last class. We're going back and seeing that when they actually were designed, they were constructed as models of mammalian vision. And so this is what they consist of. A convolutional network comprises convolutional and pooling layers. The convolutional layers are the S layers, and the pooling layers are the C layers. Because the convolutional layer is basically scanning the previous input, previous outputs, and the pooling layer is looking at groups of cells from the groups of responses from the convolutional layer and just pooling them and picking the largest value. And the convolutional and pooling layers can alternate. You can also skip the odd pooling layer, although you can't have, it doesn't make sense to have multiple pooling layers in a row and skip the convolution. You can't keep cleaning up iteratively, that doesn't make sense. And only the convolutional layers, the final layer outputs are flattened and passed to an MLP. And only the convolutional layers and the final MLP are learnable, okay? So, and pooling layers are fixed and generally not learnable. We'll see why I say generally. So how does the convolutional layer work? A convolutional layer comprises a series of maps corresponding to the S planes within an S layer. They can also be called feature maps or activation maps. So if this is the previous, if this here is the set of planes from the previous layer, then within any particular plane of the convolutional layer, in order to compute the values, it's going to be operating simultaneously on all the planes of the previous layer. And so it's going to have responses. This guy is going to have some responses from each of these planes, right? And then once it's done that, within that response, there are two steps. First, it computes an affine value at each location. And then those affine values are put through an activation function. So I'm going to call the first one, the computation of the affine value is what is called the convolution. The activation is just a step-by-step, element-by-element process, right? And so I'm going to call them affine maps and activation maps. So the affine map is computed by looking at all of the layers of the previous, all of the planes of the previous layer simultaneously. Now, a term that we use in modern terminology for these planes is channels. But when you hear the term channel, you have to think of S-planes in Fukushima's model. So just look at the highlighted S-plane on the top left. It is simultaneously responding to all of the planes in the previous layer, right? I'm still only looking at the affine computation. So let's just look at what now the actual affine value is a literal summation of the responses to all of the planes, some responses to each of the planes in the previous layer. So let's look at how it responds to just one of the planes, right? So how does that yellow highlighted plane, how is it, what is the contribution to the yellow highlighted plane of the plane highlighted in orange? So this is this figure to the left. The green figure shows the orange highlighted plane, just the single one, right? And now what you are looking at, it's an affine computation, right? So if I'm looking at this plane, so if I'm looking at a plane to compute my new S-plane, now there are several of these. This cell is looking at all of these terms, right? And corresponding to each of these, there's a weight. So the orange box shows the weights. And so to perform the computation, just the contribution of this one box, and I'm just showing binary values because this is a very famous example that I found on the web. It's very illustrative. You just position that filter. We call it the filter, but it's just the set of weights on the top left corner. So the numbers in red show you the weights. The large numbers show you the values on the underlying plane. You perform an element by element product. So it's 1 times 1 plus 1 times 0 plus 1 times 1. You sum them all up. There's also a bias because it's an affine term. And that sum goes into the top left corner. And then the filter is going to be the set of weights. The scanning, right, is going left to right, top to bottom. And at each position, you're performing an element-wise computation and summing them all up to compute the final plane. So easy enough. But that's just the contribution of one plane, right? That's just the contribution of one of these planes. What is the net contribution of all of these planes? To see that, you actually have that computation, a similar computation being performed over all of the planes. So, or the channels, if you prefer that term, right? So now when I'm trying to compute this first output map, activation map, for this guy, corresponding to this guy, I'm going to have one set of weights, also called filter parameters, with respect to each of the planes. And they're not all identical. The set of weights for each plane are different from the weights from every other plane, as you can see from the color code. They're all going to be different, right? And so to compute the term, the first affine map, I would place this filter on the top left corner. Actually, so this one, the yellow, shows this guy is showing you this orange map. And this figure here is showing you this plane highlighted in yellow, all right? And we are showing you how we are going to compute the yellow highlighted plane from all of the planes in the previous layer using this particular set of weights, also called a filter. You place them on the top left corner like so. Then you have an element-wise product of the underlying plane value and the filter value, and then you'd sum them all up. There's also an additional bias that's going to give you that first term. Then you'd slide forward by 1 and repeat the same process. And again, at the new position, you have an element-wise product and a sum, right? And so you can keep doing this, and that actually fills out the entire plane to the right. That computation makes sense to all of you? Yes or no, guys? Okay.
Why do we have different filters for just the plane in the convolution?
You're saying that, so over here, where is my eraser? That's just one filter. The set of them is one filter. Okay, just to be clear. So in the previous layer, you have many planes. Now, if I want to compute this guy, I'm going to need how many, if each of these is a 3 cross 3, how many distinct set of weights will I have? How many elements is it actually reading to compute it? 9. How many weights will I have? Are they going to be identical? 3, 3, 3. That's what the figures show. Make sense? Right? Everybody get that? And so that's just for the first plane, right? If I want to compute a second plane, I'm going to have a second such filter. And the filter itself is going to have as many planes or as many channels as the number of channels it's looking at. You get that? And so the number of channels in each filter is going to be the same as the number of channels in the input to the layer. And the number of filters is going to be equal to the number of planes that the layer generates, the number of output channels. Each filter is generating an output channel, and each filter has as many channels, as many planes as the number of input channels, right? And so the second filter would now be imposed on this guy and compute the entire second plane. Now, is this making sense so far to everybody? I'm just going to speed up through the rest of it. Yeah. Question, yes.
So once you compute the everything in the first layer, you're using like another rectangular shaped filter. So does that mean that the results are also like ordered in some rectangle?
So look at this. Look at how you're scanning this, right? The filter is shown to the right. If I'm scanning left to the right, the output map must have the same shape as the input, must it not?
Okay, yeah, makes sense.
Right? Same thing here. And here's a different way of looking at it. Instead of having all of the planes lie one below the other, I can stack them up in the form of a cube. And then the filter is also going to be a cuboid, right? I've just stacked them. Instead of showing them one below the other, I've stacked them up, and the filter is going to be a cuboid. And now a different way of visualizing the computation is to say I'm placing this cuboidal filter on top of the stack of channels. And now I'm actually, the actual arithmetic within each channel, you're summing over the little square, and then you're summing across all of the channels to get that single affine value at the output. And then you're scanning left to right in that manner to compute the entire output plane, right? So the size of the output depends on the size of the input, the size of the filter, and the stripe, right? And may not be identical to the size of the input for all of these reasons. And you have one, so let's see exactly how that affects things. Here again was the previous example, right? So if I were scanning forward, if I were taking a sliding forward with a stride of 1, then what is the size of the output going to be? So let's say my input is 5 cross 5. And my filter size is 3 cross 3, right? I can position it here, and I get one output value. Then I can position it here, and I can go get the next output value. I can position it here, and I get a third output value. But then when I position it in the fourth place, my filter falls outside the input, right? So how many positions can do I actually get? If this is with 5, and this is with 3, I only get 3 positions, right? If I go to the fourth position, I fall off the edge. Or in general, if this is with n, and if this is with k, how many positions will I get? N minus k plus 1, right? Because beyond that, I begin falling off the edge. And so you actually have the output size of n minus m plus 1. Now, and so this means you're going to lose stuff from the edges, right? And how many rows are you going to lose? K minus 1, right? Because there's the first position, yeah, and then you can slide forward n minus k. So the actual output size is n minus k plus 1, and the original input size was n. The difference is going to be k minus 1, right? So that's how many you will lose. And suppose you don't want to lose things on the output, then what can you do? You can allow it to keep going past the edge, right? Until it completely falls off the picture. And for that, you would have to pad this thing with zeros. And typically, you would pad it with zeros in a symmetric way. You take k minus 1 rows of zeros and k minus 1 columns of zeros and pad them up. So that's the convolution layer. That's just going to compute the activation map. Then the output of the activation map is put through an element-wise activation. So that's just going to compute the affine map, right? The convolution. And the output of the, yes?
What do you mean by we're going to lose the information? Like,
You don't lose information, you lose size, right? And sometimes you want the output to be the same size as the input for whatever reason. Typically, if you want to look at the output and say, where did it happen in the input, then you want the sizes to match. And at each layer, you're going to lose some columns and rows. So if you have a great many layers, eventually you're going to end up with almost nothing. You want to prevent that, then you pad with zeros, right? And once the affine values are computed, you just compute a pointwise activation to get your activation maps, right? And there's pseudocode for it. At each segment, you first compute your affine value, and then you compute your activations. So the convolutions, the summary of convolution is that convolution layers scan the input using a bank of filters. A filter is just a neuron in a scanning layer. Each filter jointly scans the maps in the previous layer to produce an output map. You can replace the word map with channel to stay with modern terminology, right? And you have as many output maps as filters, and the filters have as many channels as the input number of input maps, right? And you may have to pad the edges with zeros to prevent a shrinkage of the maps. So there's the other component. That was just the convolution. Then there's pooling, right? What does pooling do over here? Pooling is typically max pooling, as originally defined by LeCun, and they often alternate with convolution, but it's not necessary. In this figure, for example, I have two convolution layers without a pooling layer in the middle. So here's what the pooling layer does. The pooling layer actually operates channel-wise. So on each S-map, you're going to perform pooling locally to get the C-map. The C-map looks at each C-map, as we saw, only looks at one S-map. It doesn't look at the rest of the S-maps, right? And so you'd have a window, your cleanup window, so to speak. And that within that cleanup window, you're going to pick the largest value. And so here, for example, let's say the top four elements are 6, 1, 3, 1, 4, and 6. Then the largest element is 6. So the element you would pick up is 6 and copy it over. Then you slide over 1. Now it's 1, 6, 3, and 5. You pick the largest element, that's 6. And so you're going to scan, going top to top, left to bottom right. And within each window, you're picking the largest value. This is your pooling layer. Its job is to clean up. And the way it cleans up is by looking at the largest activation so that you sort of become somewhat less sensitive to smaller values that might arise from noise. And it also introduces some degree of jitter invariance, as we saw in the last class. Now, typically, pooling is performed with a stride greater than 1, not a stride of 1. We'll get back to that, right? So here's what pooling looks like. You're scanning left to right, top to bottom. And then within each window, the way we typically do pooling is you find the location of the largest and store it. That's the PIDX. And then you copy the value at that location over to the output. You need to store the location rather than simply copying the value over, because you're going to need the location index when you're performing backpropagation, right? But then you can also have other sorts of pooling. For example, instead of max pooling, you can do mean pooling, where you take the mean of the elements within that box and copy them over. So if the values are 1, 1, 5, and 6, the mean of those four values is 3.25. That's what you'd copy over. And so as you slide left to right, top to bottom, within each box, you're actually going to be copying the mean. So if you replace max pooling with mean pooling, instead of having a max operation at each position, you just have a mean operation, right? And you can have other kinds of crazy operations. Anything that doesn't have learnable parameters, like a Minkowski norm, although these are not popular, they don't do very much for you, or even have a learned parameter pooling model, which could just be a neural network. So this used to be called a network in network, where the manner in which you perform pooling is itself learned. And so this little neural network that you have is going to look at those four values to decide what the output value must be. Right? Questions? Yeah.
Any intuition to a pooling strategy?
So the original pooling strategy, the biological inspiration was as cleanup, right? And the physical interpretation is you want jitter and variance. But then once you get there, you can see, you can look at other kinds of other mechanisms for pooling, because eventually you think of it as how do I make these measurements robust? And max versus mean, they're different statistics. Minkowski norms are different statistics. Or you can have a learned statistics estimator. Yes, Katrina?
Also, question. For example, we padded with zeros in the previous layer, and then we use mean, and like if our value would change,
at the boundaries, you're going to have issues, right? So if you're using a max pooling, the zeros won't really matter, mostly. If you're using a mean pooling, yes, it will mess with the boundaries. So pooling layers scan the input using a pooling operation. For example, selecting the max from a k cross k block. Each pooling layer scans individual maps in the previous layer to produce an output pooled map. And for pooling, you don't generally pad the edges before pooling because padding makes no sense, right? All those zeros are going to mess with you. So pooling is going to operate on the output of the convolution. And pooling will always lose stuff at the edges because, as Katrina just mentioned, if I pad with zeros, I'm going to get rubbish. And so you don't want to do that, right? So here are the two kinds of operations we've looked at: convolutions and pooling, right? In each case, the way we have defined it, the stride is 1. And so the output size, if you ignore the edge effects, is basically the same as the input size if you're striding by 1, right? But you can also perform operations which increase or decrease the size of the maps. And so you want to think of these operations which increase or decrease the size of the maps as individual separate operations, right? Now I can decrease the size of the map. This is called downsampling. The way I would do this is to basically throw away every k minus 1 of every k elements. So for example, if I wanted to decrease the size of the map on the left by a factor of 2, then I'm going to block out every second column and every second row, and then only retain the remaining values. So this is reduce the size of the map by a factor of 2 in every dimension. So we can think of this as a downsampling layer. And from a mathematical perspective, it makes a lot of sense to think of downsampling as its own operation, as a separate layer. But then, when you're actually, basically you're reading every nth element, every nth row and every nth column, right? But implementationally, it doesn't make sense to compute things that you're going to throw away. So it doesn't make sense for me to convolve with a stride of 1 when the subsequent layer is going to throw away every second element. So instead, if I'm going to have a convolution and a downsampling by a factor of 2, it makes sense for me to instead say I'm going to perform convolution with a stride of 2, right? If I'm going to be performing pooling and then downsampling by a factor of 2, it makes sense for me to say I'm performing pooling with a stride of 2. And so you can merge a downsampling operation with the previous operation, whatever it might be, and perform the previous operation with a stride greater than 1 to get the reduced map. Right? That makes sense to everybody? Right? So that's what we typically do when you're implementing things. But conceptually, it's very useful and convenient to separate the downsampling from the previous operation. Although implementationally, you might actually just have a stride greater than 1. And this is going to be particularly important when we're performing backprop, right? So downsampling after convolution is like saying I'm performing convolution with a stride of 2, right? And if that's going to reduce the map size, the output map size by a factor, which is the stride, right? The actual arithmetic is on the slide. Same thing, so that's convolution with downsampling. If I wrote the code out, all that happens is that within the loop, I'm going to increment the index by the stride. Downsampling and pooling, same thing. If I have pooling followed by downsampling, I can merge the two, which is like saying I'm going to be performing pooling with a stride of 2, right? And so once again, all that happens over here is that within the indices, if you're writing the code, the indices are being incremented by the stride. again, the operations remain the same. You have to store the index. If you're performing max pooling, you have to store the location of the index where the largest value happens, and then copy the value over there over. Now, same thing with mean pooling, right? All of them have the same concept. And so typically, if I've got an n cross n picture compressed by a p cross p pooling filter with a stride d, then basically you're going to say, except for the edge effects, the downsampling is going to shrink the image by size t. Now, the reverse of downsampling is upsampling, where you increase the size of the layer. And the way you increase the size of the layer is very trivial. You do the exact opposite. In downsampling, if you are downsampling by a factor s, then after each column, the next s columns were replaced by zeros and then thrown away, right? After each row, the next s rows were replaced by zeros and then thrown away. In upsampling, we're going to do the exact opposite. We are simply going to introduce s minus 1 columns of zeros and s minus 1 columns of rows of zeros between rows and columns. So this is all you do. This is literally all you perform when you are performing upsampling. You spread things out and introduce zeros, right? And so if I'm performing upsampling, upsampling is an operation all by itself. It's a trivial operation. You're literally just expanding the picture by introducing zeros. But then, if upsampling is followed by convolution, those zeros will go away because the information gets spread over all the zeros by the convolution operation. It does not make sense to follow an upsampling operation with pooling, because the pooling is simply going to keep sucking up the zeros and throwing away useful information. The only time you perform, only operation that can follow an upsampling, the operation that must follow an upsampling is a convolution, right? Upsampling is also not useful as the final layer of a CNN for the same reason. You're not really adding any information, right? So here's the upsampling layer. You just sort of allocate a larger picture and then copy things over the rest of zeros. So terminology-wise, if I'm upsampling by a factor s and then following it up with convolution, people like to call it convolution with a stride 1 over s. So if I'm upsampling by a factor of 2 and then follow it up with a convolution, then it's sometimes referred to as convolution of with stride 0.5. There's no fractional stride. All it means is that the image has now been expanded by a factor of 2 in each direction by inserting zeros, and then now you have a regular convolution. Right? So these are the resampling layers. In summary,
could you explain the intuition behind upsampling?
Okay, so the intuition behind upsampling is particularly useful when you're trying to reconstruct stuff. Now, what happens is that as you go through the layers, the maps keep getting smaller. Now, in many situations, you might want to go back from the smaller map back to something the original size. And so you want to increase the size all over again. So upsampling is most commonly used when you're trying to reconstruct things. But you can also think of upsampling as, just as you can increase the number of, you can have more neurons in any layer than you have, than the size of the original input itself. You can analyze a 100-dimensional input with a layer of 1,000 neurons, right? So upsampling, you can think of upsampling as something like that, where you're scaling up the input so that you can analyze it better. That answer the question? On Zoom? Okay.
Yes, I have a question. Actually, it is about the pooling, but why is the max pooling commonly used than others?
Empirically, it's just found to be the best thing. Simply because, there are a couple of different reasons. One of them has to do with backpropagation itself. But empirically, if you're cleaning up, finding the max, which also has the biological basis, has found to work better than the rest. In fact, in the latest architectures, we don't use pooling layers at all. Right. So map sizes can be changed by downsampling or upsampling. Downsampling typically follows convolution or pooling. Upsampling occurs before convolution. So downsampling occurs after an operation, upsampling occurs before an operation, right? And you can look at it differently. You can think of an operation followed by downsampling if you look at it the reverse way. If you inverse the order of operations, then you get an upsampling being followed by an operation, right? Yeah. Lawrence?
Must you like upsample just zeros? Could you like something else?
Pardon me?
Could you insert something other than zeros?
You could, but then you expect the filters to figure out what must be done. I mean, a more reasonable thing would be to do a linear interpolation between the nearest pixel values, right? Nearest values. And yes, you definitely could do that. And these have been tried. Sometimes they work nicely, but more often than not, you just let the filters figure out what they must do. And so, to add to our story, CNNs are supervised versions of a computational model of mammalian vision. They include convolutional layers comprising learned filters that scan the outputs of the previous layer and pooling layers that vote over groups of outputs from the convolutional layer. Convolution can change the size of the output, which can be controlled via zero padding. Pooling layers may perform max, p norms, or be learned. Resampling layers increase or decrease the size of the map. And downsampling can be merged with the preceding operation by simply scanning with a stride greater than 1. And upsampling must occur before the convolution operations, right? Have a pool, all. Pokemon Lantern, when the time's up, that's going to be your turn. Okay, time's up. So Pokemon Lantern, what's the answer to the, is the first statement, upsampling by S introduces S minus 1 zeros between adjacent rows and columns. Is that true? Is Lantern around? Yeah, true, okay. Pokemon Wurmple, upsampling layers are generally followed by pooling layers, true or false? Wurmple's absent. Staryu, Pokemon Staryu, upsampling layers are generally followed by pooling layers, true or false?
False.
False, okay. And Heracross, upsampling layers are generally followed by convolutional layers, true or false?
True.
True, okay. And Aerodactyl, upsampling layers can be combined with the convolution or pooling layers before them into a single operation with a fractional stride. True or false? Okay. Igglybuff, what's the answer? True. False, right? Fractional, there's no such thing as a fractional stride except in terminology. What about the second one? Downsampling by S replaces every S row and column with zeros. True or false? That's what Zapdos.
False.
Okay. Downsampling by S deletes S minus 1 consecutive rows and columns and retains every S row or column. Pokemon Paras. True. Downsampling layers are usually merged with the convolution or pooling layers after them, which are then modified to convolution or pooling with a stride. Tentacool?
False.
Okay. We got to fix the Pokemon names. And downsampling layers are usually merged with the layers before them, which are modified to convolution or pooling with a stride. Smeargle. Pokemon Smeargle. No? Pokemon Doduo?
True.
Also no? True. Okay, thank you. So, you guys were right. So I'm going to spend a quick 2 minutes putting everything together, right? So all the things that we've seen, I'm going to be assuming max pooling. Here's how we would put them all together. Let's say you're analyzing an image. So an image has, a color image would have multiple sub-images, red, white, and red, green, and blue, right? So you can think of the input as having 3 layers already, or 3 channels, which you can stack up. You're going to have a bunch of filters. Now, each of the filters is also going to have 3 channels, and it's going to have a face. And the face can be any size. Typically, the number of filters is a power of 2, and the size of the face can be 5 cross 5, 3 cross 3, or even they've got to be small enough to capture the fine features, particularly important for scaled down images. And 1 cross 1, what is a 1 cross 1 filter? It's looking at one, that's an undistributed, non-distributed scan, right? Whenever you're looking at broader regions, it's a distributed scan. When you're looking at a 1 cross 1, that's like a non-distributed scan, right? That's one layer of non-distributed scan. And so that's a 1 cross 1 filter. So these filters would each compute for the parameters to choose would be the number of filters, the size of the filter, and the stride. And so these, and whether you're going to 0 pad, each of these filters would then result in 1 output channel, right? And that's just the computation of the channels is shown. And then, so the total number of learnable parameters over here is going to be the number of filters times the size of each filter, where each filter is going to be L cross L times 3, because there are 3 input channels, right? And this will be followed by a pooling layer. And for the pooling layer, the operations to decide are the size of the pooling window and the stride and the type of pooling, right? So, and the operations when you're actually pooling at, remember, for max pooling in particular, you always first find the index of the max location and then read the value from there, because this is going to be required for backprop. And so the output of the max pooling is going to be a bunch of bunch of channels, which are, we're going to have as many channels as the number of filters in the previous convolutional layer. It's just that each of these maps is going to be smaller than the convolutional maps themselves, because the stride is typically greater than 1. And jargon, these filters are also called kernels. Convolutional filters are also called kernels. We like to have lots and lots of jargon. So, if you come up with your own and you manage to popularize it, you become famous. And then from those, you're going to have a second bunch of filters, where now the number of parameters in the filters, each filter is going to have as many channels as the number of filters in the previous layer. Why would that be?
You're learning something different.
Why would that be, Pokemon Mareep? Or Pokemon Natu? Why would that be? Pokemon Gyarados. Missing. Okay. That's because the number of filters in the previous layer decides the number of channels that the previous layer outputs, right? And so the number of planes depends on how many filters the previous layer had. And so the next layer's filters are going to have as many planes as the number of filters in the previous layer, and they have their face. So the parameters to decide are basically the number of filters and the values of, and the face of each filter, and all of these must be estimated, right? And the design decision is going to include the stride, whether you get to 0 pad, and all of that. And then you'd have the subsequent pooling layer. Again, you're going to be deciding the size of the pooling window and the stride. And you can keep repeating this. And eventually, at the end of it all, you're going to have an MLP. And for the MLP, the things to decide are how many neurons and how many layers, how many neurons in each layer, and their activations. So each convolution layer with stride 1 typically maintains the size of the image, except at the boundary. But each convolution layer will generally increase the number of maps. Each pooling layer decreases the size of the maps, and because they typically have a stride greater than 1. And within any given layer, the filters must all be the same size so that the things sort of line up. But different layers can have different numbers of filters. We'll spend a few minutes in the next class talking about the relationship of the number of layers and the number of filters to the size of the input itself, right? And so all of these things are parameter choices. I'll actually have a final poll before we close. Okay. I'll stop that early. Does anybody want to answer this question? They're the same, right? And since I'm here, just a minute more. Give me one more minute. How do you train these models? We're going to spend the next lecture on training the models, but we are performing backprop. You're going to be given inputs with labels, so the network will generate output labels, right? And you can compute a loss from the between the output and the target output, and that loss can be differentiated, and those derivatives can be passed backwards through the MLP, just like in a regular MLP. And so the MLP parameters can be learned, trivially enough. But then you also must learn the weights and biases of all the filters and all the layer. And here's where the fact that they are shared parameter networks, right? So you compute the divergence, and these derivatives can be passed back. This is just the usual stuff. And the derivatives can be computed all the way till here. And then when you want to compute the derivatives going further back from the MLP layers, you run into problems, right? We have to think harder about how well that is done, and that's what we're going to talk about in the next class. Thank you. I'm sorry about going over.